Let's continue with the next talk. So the next talk is on constraints on inflation, strings, and exotic models. It will be presented by François Bouchet from the Institut d'Astrophysique de Paris.
All right, so I will be continuing now and turning on to what Planck has to say about the early universe. And I'm drawing from the content from actually 3 big papers, and that will be continued by about 10 speakers during the following days. So it's more like an introductory overview of what Planck has to say. And, well, our window to early universe physics is essentially this beautiful map. And as you all know, well, we have a pristine view of the initial conditions on all scales larger than 1 degree, and then something slightly transformed by linear physics, mostly, on smaller scales. Now, of course, we have to characterize this random field, we are using a number of statistical tools. This is the one that George has been essentially describing. But there is another one, which is a 3-point statistics. And all the previous plot is trying to tell you, I think of it as, you know, what you have to do to describe what is happening in 2 different points on the spheres. Well, the next level is to have 3 points on the spheres. And to do that, you need to have 3 numbers. And these are, you can think of these as these 3 axes, 3 multiples. And so we are just showing the contours there are just, if you want, the value of the 3-point function as a function of these 3 numbers. And so this is sort of a complementing, adding some more information on the top of this one, which is 2-point statistics, by all what we can extract from this. And I'll be making a lot of use of this. Now, George already told you, and one of the main results there is that the base Land-Basilean model fits very well. And when we pull BAO in this is like a 7 sigma detection ruling out of the Harrison-Zeldovich scale invariant spectrum. And I will also return to this. This is this tension, and we'll see that, as George already alluded to, we'll see that a number of the extensions that are providing marginally better fits are actually driven largely by this. Now, we all know that inflation has developed a few variants from the early days. And so we find ourselves here with at least trying to use the machete here is actually these 2- and 3-point functions. Now, despite this sort of jangle-like, there is a simple reference model. And this was introduced very early on. And this is essentially a spatially flat universe, a single inflattened field, which is obeying slow roll in conditions, which is essentially that the potential has small derivatives, that this is actually obeying standard physics, that there is no funny kinetic terms or higher order, and that the initial conditions at very early times behave as in flat space. When you put all of this together, you expect to have essentially one mode, which are adiabatic fluctuations, which is all the part of the various components fluctuating together. The power spectrum, the initial one, which is underlying, which is giving rise to both the 2-point function, is described by a single power law, which is smaller than 1, no running, a number of E-folds till the end of inflation between 50 and 60, and negligible non-Gaussianity. So, of course, the next step is just to sort of challenge all of those and sort of see, well, how solid is omega k ns? Is there any variation of ns versus scale? Are there indication of non-slow roll features in the power spectrum that may have been escaped? And we'll do both parametric and non-parametric. Could there be isocurvature fluctuations, defects, and LEO for a local, equilateral, and orthogonal non-Gaussianity, or even further? So now, in the collection of inflation models, quite a number of those which are still with us today and which are in the slow roll approximation and good to sort of compare to data, were already there very early on in the 80s, as soon as the inflation ID came about. And well, you can see names and dates, and this is essentially most of the 80s. I stopped naming at 83. Otherwise, I would have a full book. Anyway, so here are the specimen. And when you look in this NS versus R, or tensor to scalar ratio, this is how they fit. And you clearly see that there is already quite a bit of tension for some models. There is a tendency to prepare concave models, and like hilltop will be pretty natural. On the other end, like chaotic inflation with high powers would be not favored. So this is a sort of standard plot, but then we can go a little bit further than that. And so we can ask, well, for all of these models, we have other parameters which haven't been explored very much, which is how the end of inflation happens till the time of all particles are being generated. And this can be one way to parameterize this is with a sort of an effective equation of state, W in here, between the end of inflation and thermalization. And so you can use this as an extra parameters and look at the various parameters of inflation, and you start seeing the constraints that Planck is putting on there. So we are pushing the various free parameters, if you wish. Now, about running, George already said that we are not at the level where it would be really constraints. For instance, here is a prediction. The purple one would be, simple monomial chaotic inflation model would see very, very small, would require much higher precision. So at this level, there is absolutely no need. Now, one reason why one may want to introduce running would be to have open models of inflation. I mean, there was quite a bit of, for a while, there was these Baroque models which were trying to say, well, after all, if omega k is proven to be non-zero, well, inflation can go with it. Well, the price is, of course, to have running spectral index and tensor to scalar ratio, and now, large ones. And what you see is that there is absolutely no need for that, and this is all compatible with omega k being 0, and happily fitting there with no running at all. Of course, our patch of the universe might still have a fluctuation, from a much larger scales. But in that case, this is omega k of the order of 10 minus 5, right? So even now, even with the precision of Planck, we're not probing this. Okay, so one thing we can do is actually to have an attempt at, rather than trying to have a potential that is fitted at all scales, is just to reconstruct the potential over the observable window that we have. And for that, we can do a Taylor expansion around the pivot scale, and just look at the results versus the order. And here are a number of best fitting models and a collection of them that would all fit the data reasonably well. And what you can sort of see there is when you go to fourth order, quartic potentials, it develops a tail there. And what this tail is doing is actually giving you something that is not described by slow roll, which is actually helping to fill the smaller scales, this tension that we've seen before. So this indication is precisely what is being pulled by these low multiples that we've discussed earlier. Now, another thing that one can be doing is actually to sort of try to see whether there might be features in the initial power spectrum now in K. So what you do is essentially you are trying just to reconstruct how much power there needs to be on the various scales. And then you penalize this you don't allow for arbitrary oscillations, of course. And this sort of rigidity is given by this smoothing parameter. So at large smoothing parameter, you don't see very much. But when you allow for really very localized features, then you find that there are some indication that the 3.1 sigma that George was alluding to for k equal 0.1, essentially where you see some pretty localized feature, and to a lesser extent here. Now, let's take this particular curve, the red curve, and just say, what is it doing to the power spectrum? So here it is. So this is just a translation of this best fitting model on the CMB, on the CL at the various frequencies. And this is a feature that we're talking about, which is at k equal 0.1. This is what is being driving this feature in the potential. And we've looked very carefully at this, and we spent a lot of time trying to see whether there would be any indication of systematic effects and so on, and we didn't find any. Now, clearly this is an area where having more data and the ability of doing a different null test, having redundancy to making further cuts on the data will allow us to sort of confirm or infirm the significance of this feature. So this is borderline. This is something that is a 3 sigma level, which we cannot either pull away or decide it's insignificant. So that's the status where we are at. Now, we can also make some search, which is rather than just doing non-parametering, trying to find the power spectrum mode by mode, you can look also at the collection of models which do have features. So here is a Wiggle model, which in log k, which has any process that would be periodic during this exponential inflation that would naturally do something of that type. Step inflation, if anything, would happen at some point during inflation. And so what is done there, of course, those introduce extra parameters as compared to a simple power law. So what you can do is actually run through these parameters. So you are actually allowing for a full zoo of models. And then look at those which have a posterior probability that is best, like for instance there, cutoff model, or some of them. You can sort of see that there are some cases where you find some models fit somewhat better. Now, here are the best fit models. So here is a power spectrum that would be just non-scale invariant with NS maybe of 0.96. And here is the best fit. That is to say, if I'm using this parameter, or this parameter, or I guess this parameter, right, for this particular model, this is what you find. Now, how much better this is? Well, you can compare directly to the power spectrum level, and you can judge for yourself the significance. Now, of course, what we've done is we haven't done a full frequentist analysis, but we did do, I mean, our base estimates tell us how likely this is. And in fact, this is only, I mean, this is not, once you account for the fact that we've searched a full collection of models, well, this is not very significant. And of course, this is tantalizing, and there we have means to actually go after that, which is these models would have a signature in polarization and also in non-Gaussianity search, and so I'll turn to this in a minute. Isocurvature modes. Well, as I told you, inflation has naturally adiabatic fluctuations, which all the components are actually locked together. Isocurvature modes arise when there are spatial variation in the equation of state or velocity field between the different species. So that they have zero curvature, but they are distributed in different ways, like strings would be an example of that. So here are various contributions that one may have, and they are not in phase. And so here are different contributions. And these might be having, well, if you don't specify a theory, you would have arbitrary correlation between all of these various components. What we've done, and without the help of polarization, we did a more reduced analysis, which is just to look at what happens if we introduce one single isocurvature mode. And there again, I mean, well, you can sort of look at how much isocurvature, how much power coming from isocurvature fluctuations could be hidden in the various L range. And this is very small. So there are pretty weak evidence of any isocurvature. And of course, there are some specific, like curvaton or axion, are actually quite of interest, but there is no strong evidence. And when there is some, once again, you can sort of see where this is coming. It's, once again, you are being pulled by this low L deficiency, well, deficiency of power as compared to the based lambda CDM model. So this is a running theme there. This low L part is actually driving a number of the extensions, as George was saying earlier, to actually try to fit that barrier. But actually, the interesting thing is none of the collection of models we search for is actually bingo on the top of it. So it's actually even more surprising because it might be even more radical than what we need than any of the models which are sort of slightly being pulled but not actually doing it right. Now, as another hypothesis that we want to check is the presence of cosmic defects, which are a pretty generic outcome of symmetry breaking phases. I mean, transitions associated to symmetry breaking in the early universe. And of course, in the 80s, this was proposed as an alternative to inflation to generate initial conditions for structure formation. Well, we know from the turn of the century that this cannot be the case. We do see the adiabatic fluctuations, and that was the end of it as a theory of structure formation. Still, they are pretty natural, and it's interesting to see whether we see any indication of strings, and if they were detected, they would tell us, in particular, the particular pattern of succession of symmetry breaking that leads to our current universe. Now, strings, or, well, in more general speaking, defects, affect both the power spectrum and the non-Gaussian properties. There are still some difficulties in making absolutely precise predictions about the power spectrum from strings, and this has to do with the complexity of the calculation. And there are two types of calculation, and they correspond to, including or not, some radiative effects. So we've decided to show all of them essentially. And so here are the case of three types of angular power spectrum from strings that will be an additional contribution to the adiabatic one. And here is an additional comparison with global textures and semi-local strings. So when you do this, and this is uncorrelated. In that case, this is uncorrelated because this is happening differently. So you just see how much you can hide in the power spectrum that has this shape and still have a decent shape for the rest of the cosmological parameters. And the answer there is not much. And this is about 2 times 10 to the minus 7 for g mu over c squared, which is the mass per unit length of the strings, but which has a direct correspondence to the symmetry breaking scale. And translated, this means that this has to be for Nambu-Goto strings smaller than 5 10 to the 15 GeV. In that case, this is interesting because we're sort of bounding things from above and not from below, as we do from usual particle physics. Now, this is on the power spectrum. Of course, strings are also providing some non-Gaussian signature. And we've also run within Planck some of the largest simulations ever to be able to do the confrontation. But at this time, what we find is that the constraints that one gets by searching for those patterns in non-Gaussianity are actually weaker than the straight ones that gets from the power spectrum. So this is consistent, but the constraints there are more like 8 times 10 to the minus 7 rather than the about 2 times 10 to the minus 7, because that includes only some part of the fluctuations, all of those that are happening between the last scattering surface and us. Now let me return to the Planck CMB bispectrum. Now this can now be used essentially to try to do fingerprinting. I told you in the sort of minimum model where we have a single field, this is not only adiabatic, but under pretty broad conditions, you can say that there should be essentially no substantial non-Gaussianity. So any detection of a primordial origin of this would be really very, very interesting. And it turns out that there are generic shapes that can be generated by categories of extensions, if you wish. For instance, if you see something that has an equilateral shape like this one, then this is a kind of thing that can be described and are expected to be found in these extensions on inflationary theory. Orthogonal types, I mean, which are different patterns, come from or will be the signature of a different category. So in other words, we can use these patterns as an indication to the class of theories that might be needed to go further than the sort of the minimal inflationary model. So those, I thought that these are just the most common ones. the local, equilateral, and orthogonal. So in my bestiary, I call this Leo, and I will compare Leo versus non-Leo. So these are the first, of course, these are just the late time, that is the CMB imprint in terms of bispectrum. But what this is generated is actually coming from the bispectrum at the time of inflation, or whenever this was created. So we searched for not only those, but we also looked at the addition of a number of other cases which have comparable but not exactly the same initial, three-point function in space. One thing that is interesting is, so this local shape, of course, let's take, for instance, this one. There is a parameter, which we'll call F and L, which sets the overall amplitude of the pattern, right? I mean, one thing is to have the shape, but the other thing is to have the overall amplitude of it. And so when we're looking at a shape, we're putting constraints or making a measurement of this overall amplitude, which is called F and L for F nonlinear. So here is the WMAP result, which was a little bit on the high there. And this has been now, we have a much smaller value. And this is how the value goes when you increase more and more modes. And so you decrease, of course, cosmic variance. And at some point, you hit the point where even Planck is losing it in terms of signal to noise. So you see that, well, we have quite a stable value there, which is around 10 before correction for the ISW cross-lancing bias. And that also explains that why WMAP was finding it a little bit high, because this was just the fluctuations, which is due to large scales. Now, we've done an extensive analysis using different component separation methods, using different estimators, doing all kinds of null tests. In the end, here are the Leo constraints. So on the local, equilateral, and orthogonal, here are the values which are just all consistent with 0, with much smaller error bars than they were before. I mean, for WMAP, this number here is about 21. So this is at least 3 times tighter. Now, of course, as I said earlier, one thing is to go for Leo, which is a well-known animal, but we might actually go for wildebeests. And so try to search the savanna. And so we looked for specific shapes. And for instance, for all flattened shapes, when you do the full analysis and look at all the variations, like being a vacuum state, which is non-Bunch-Davies, looking at non-canonical, looking at, various extensions. I don't want to get into this. You find no results whatsoever. I mean, no better fit. On the other end, with some feature models, and there again, going through a big grid, so you're trying to find a lot of possibilities. There is one case which speaks out, which is a 3.2 sigma tentative detection. And here is a hint. So you see here what the data is. So this is the best description that we have of a visualization of the 3-point function of the CMB. And that's, for instance, one of the feature models where this one, very specifically, which has these particular characteristics. And of course, I mean, you can immediately see, I mean, there is some similarity and so on. So now the question is, well, how significant is there? And of course, we looked through a large number of models. So you do expect at some point to get matches like this. In any case, this is also a running theme. I mean, this search is really very much sort of look at the territory and see what is interesting and what needs further analysis. And that's what we're doing. We're not claiming that this is it, but we did find some indication, some path for further research. This is clearly one of them. Now, one of the things that we now can do with the sensitivity of Planck is to start looking at joint analysis of what the power spectrum NS constraints, as well as the non-Gaussianity search are telling you. And we have already a number of results there, which I will not get into the details, but some models are actually getting out of this in pretty bad shape. So specific models, for instance, of K inflation, well, you find that there is essentially no more room for them. If you put together what non-Gaussianity, lack of detection, as well as constraints on NS are telling you, well, this is essentially no more window for this particular class. Ekpyrotic, as another, which is actually an alternative to inflation, is a little bit of a different case because there are some flexibility in the theory, let's put it this way, in terms of the prediction it can make. So one mechanism, which was called conversion mechanism, and I don't, was already sort of constrained by the previous analysis from WMAP. Well, now this is decisively ruled out. But now even the sort of newer scheme of kinetic conversion now is essentially dramatically reduced, and there is very little space left for that approach. Now let me just spend a few minutes on the conclusions. As now, if you look at what I told you during this 30 minutes is that we have no indication that there is any need for curvature, no LEO at all, no evidence for defects. On the other end, a pretty solid evidence that we are not scale invariant, that NS is around 0.96. No evidence for running. We can put constraints also on the inflation energy scale just by the upper limit on the tensor to scalar ratio. And so, and I won't read all of this, but the point is, in the end, we've looked at a full collection. We find a beautiful agreement between the CMB data and the best, simplest model. On the other end, there are essentially two categories of hints or tantalizing hints, and they are at low L and high L. And at high L, what I told you was essentially, well, mostly around L of 1800, which can be related to this K equal 0.1 feature. And there we're blessed with a lot more data coming in and no cosmic variance limitation, and we are pretty sure we'll be able to tell you more about this. On the other end, on the low L side, you've seen that this is driving a lot of these extensions at small level, and small just because these extensions don't do exactly what is needed to account for that. And so there we're hit by cosmic variance, and this is not very significant. At most, this is a 3 sigma result, and the question now is to what extent can we strengthen this? And so the only way that this can be strengthened is within theory, whether there is a natural theory that explains this and makes prediction, say in polarization or some other part of the data that we can actually go and look for. So we'll be working hard on trying to look at this, but we're listening to you two to see what proposals you will be making. Thank you.
Questions?
Yes, should I? Any question?
Yeah, just stepping in on your last remark.
Thank you.
Okay. Yeah, you're saying new data, but it's also known that lambda CDM has some troubles at smaller scales. Oh, sorry, at scales of galaxies and inside the galaxy and so on. You could also say that it becomes time to get worried about those troubles.
Sure, but then this is a... I did spend a few years working on galaxy formation and so on, and that was the reason why I escaped to Planck. I'm all too aware that what we are finding there is gastrophysics, and there are many ways, I mean, many difficulties along the way to confront, our simple models to all the way to the galaxy properties. So yes, we've seen some tension, but there are quite a number of ways out. And I think as far as I'm concerned, I'll be more keen on analyze the polarization data of Planck. Sorry. I'm not going to solve the lambda CDM potential problems on small scales.
No, but in the end, the right theory should solve everything. Let's be clear on that.
Yeah, but I mean, not everything is of the same level. I mean, for the, well, anyway, I'm not going to get into this. Yes, George, what, he wants to say something, or, well, maybe I can give you the...
any theory that explains everything is bound to be wrong, because there's always some data that is wrong.
Well, that sounds like an excellent closing.
Any other question? Yes.
What do you mean? But we standardizing him both at low, smaller than 30, multiple, this I understand, and high L, what does it mean?
Well, high L, I meant, you know, this L of 1800 stuff. You know, I mean, typically the fact that we have this 3-point-something evidence for a feature like, okay, which, as I showed you, I mean, it does fit very well some depletion in this L of 1800, which corresponds to K equal 0.1. Well, I mean, we found some similar examples of this when we account for all the correlations that there are and coming from foregrands and cuts and so on. It's not something that, I mean, you know, we were confident that this is fundamental. I mean, it may very well be, you know, this is just a statistical fluctuation. And that's, well, we have a lot more data. We'll be looking into this, and that we'll be able to nail that.
One question. It was mentioned that when you used the Planck data to clean the WMAP polarization and get another measurement of tau, there was some movement on the parameters, including the amplitude, right? Could any of this be related to the low L deficiency or affect those conclusions?
What we found is that, you know, L by L, it's all the mode, at least in temperature. We looked in great details, and we find exactly the same solution on the CMB mode, irrespective of the various, you know, component separation method we're using. So I don't think this can be responsible for that. Now, this, you ask something somewhat different, which is in polarization. The only thing we did there was to sort of try to answer to quiet an anxiety that some of us had when we were saying, well, can we actually use WMAP polarization, which is using a model to correct for dust, without having any ID, because there was no measurement before Planck on this on this high frequency part. Could it be that they got it sufficiently wrong that this might drive all of the analysis? And the check we've done, and that was presented by Paolo Natoli earlier this morning, is no, that's fine. I mean, this can be improved, and we will, but any inaccuracy there is not likely to drive any of our parameter results.
I would not necessarily put axion and curvaton scenario in the same group. I'm not saying that any of them is very natural or whatever, but I'm just saying that in the versions of the curvaton scenario, which I myself consider natural, there are no isocurvature fluctuations, so the constraints from isocurvature doesn't apply to them.
Indeed, and we did, we are, I mean, when you go through the papers, we do put separate constraints. I mean, there are, we do say that in the models where there is an isocurvature imprint, then you get the RD greater than 0.95, I think. If you remove that, then you are left with only the imprint on non-Gaussianity, and there the constraint is much smaller. I think this is RD greater than sort of 0.05 or something. And so we were careful to make that separation, which indeed, I mean, is.
Any other question? Okay, if not, we thank again to